Okay, this video is going to look at Walding Chapter 2 in text questions. This is a fairly big chapter, so we'll probably have to break it up into 3 smaller videos, so let's get started. Question 1 reads, in figure 2.5, which is below, we are asked 4 questions about the displacement and the distance. So let's just quickly draw it out. So we've got our points labelled A, B, C and D, and we're told that this is 2 kilometres, 4 kilometres and 2 kilometres. Okay, so question 1, part A, what is the displacement of the competitor at point B? So we can see here if A is where we've started, and that's a fairly reasonable assumption, that B is just 2 kilometres away north. So the displacement S equals 2 kilometres north. Now if you'd just written 2 kilometres, that would have only been part marks. If you'd just written 2, that would have been even worse. Don't forget units, don't forget directions. Now we generally put the directions after the units. Okay, B. What is the total distance travelled when at point B? Well, if he's going A to B to C to D, well, we can see it's 2, 4, 2. So his total distance, D for distance, equals 8 kilometres. Note, there is no direction. What is the total distance travelled when at point C? Okay, 2, 4. So D equals 6 kilometres. That's actually simpler than B. What is the displacement at point C? And they've given us a reminder to include the direction by stating the value of the angle CAD. So that would be starting at C, go to A, back to D. So they want us to include that angle. We could work out this angle instead. We would find it would be the complement of whatever theta will be, but we'll just go with what the textbook's asking. So if we want to find out the displacement, we can see we've got to use our 2 vectors at right angles in order to work that out. So our displacement at C is going to equal the square root of 2 squared plus 4 squared. Okay, and all I've done there is rearrange Pythagorean theorem a little bit easier, and we find if we chuck that in, we'll get 4.5 kilometres. Now the angle there, so we've got this angle and we've got this side, and we can infer, well, that's going to be the same thing as BC, so that could be 4, and you could label that in there. So our theta is going to equal the arctan again. If you're not certain, check my check my algebra for that, of 2 over 4, which would equal then 20, should equal 26 degrees. Let me double check that. Opposite over adjacent, yeah. Shift tan of 0.5, yeah, or 26.5 degrees, so I'd actually probably say 27 degrees, 26.6 degrees. Now, we need to interpret that angle, so we could say that the displacement of C equals 4.5 kilometres. The angle could be written as east 26.6 north, or it could be actually just written as 26.6 degrees, starting at the positive x-axis and going counterclockwise. We could also work it out as north, let's see, 73.4 east as well. That would give us that complement that I was talking about before. Okay, on to question 2. You watch your dog following a cat scent trail. It walks 50 metres north, turns and walks 60 metres east, and then walks 20 metres south. What is his displacement? Well, let's draw that. So, you're standing here, so let's draw us, and you've got your dog. I can't really draw dogs, so that's close enough. And he goes 50 metres north, and then he goes 60 metres east. Units. And then he turns around and goes 50 metres south. Well, visually we should be able to see, oh, okay, well that's cancelled that, so his final displacement is just going to be 60 metres east. However, let's work it out mathematically. So the displacement, or the change of displacement, will equal the 50 meters north plus 60 meters east plus 50 meters south. All I'm doing is I'm adding together all these vectors. Now, if we look at here, the north and south is opposing, and 50 meters south is the same thing as negative 50 meters north. So 50 north minus 50 north plus 60 east equals 60 meters to the east. Alright, and so there we go. The dog has gone 60 meters to the east. That direction is the very important bit. Note the distance in this case would be 160 meters. You'll always find distance is greater than displacement. A toy train is running around a circular track of diameter 120 centimeters. What is its distance travelled and its displacement after 1/2 of a lap, 1 full lap, 2 laps, and 1/4 of a lap? So we're going to work out both. So let's draw our thing first. We've got a circular track, and we know that the diameter equals 120 centimeters, which means the radius equals 60 centimeters. That's always important. Remember, you're going to have to know your formulas. Sorry, that looks a bit small on my screen. I'll make that a bit bigger. D equals 120. Yep, that's not too bad, though that 20 kind of looks like a 7. And R equals 60 centimeters. Good, that's much better. Alright, so let's say we're starting here. Doesn't matter where we start, but we needed to pick a start point somewhere. It's a circle, so they're all going to be the same. We want to know 1/2 lap, so that would be over here. 1 whole lap, that would be back here. 2 whole laps would be back here, and a 1/4 lap would be over here. So let's write that. So we want 1/2, we want 1, we want 2, give it a heading, and we want 1/4. And we want to know what is S and what is D. Now, if we think about it, D, in this case for distance, we're going to need to know, well, how far is it to go around the circle? So let's work that out. The circumference of a circle equals 2 pi r. So in this case it's going to equal 120 pi, which would be approximately equal to 120 times pi gives us 377. Just a little bit under 377 centimeters. So let's do all our distance calculations first. So after 1/2 a lap, it's going to go half of that. 377 divided by 2, 188, or about 188.5 centimeters. 1 lap would be 377 centimeters. 2 laps would be twice that, 754 centimeters. And then for 1/4 would be 94.25 centimeters. Okay, now we need to work out the displacement. Well, for the 1/2 lap, it's directly opposite. So if we take this way to be north, then the displacement is going to be 120 centimeters north, because he's just the radius away. If he's gone 1 lap, his displacement is 0. If he's gone 2 laps, his displacement is 0, which, when we get into our definition of velocity a little bit later, means that technically his velocity has also been 0, which is always an interesting bit. The next bit, though, now we're going to work out, well, how far away is it from here to here. We can see it hasn't gone the curve, so it will be slightly less. But this distance from here to here is just half the diameter, it's the radius, and so is this. So our displacement for 1/4 track is going to be Pythagorean theorem rearranged again, 60 squared plus 60 squared, which would equal 60 squared times 2, square root that, gives us about 85 centimeters, so let's do that. 85 centimeters. And we need an angle. One good little trick is, because these are both going to be the same side, shorter sides, then our angle must be at 45 degrees, and I'm going to take that as being also 45. That'll be 45 degrees in there as well as in there, so we'll just write 45 degrees. I hope you can see how that works out there. Alright, let's find our next question. The answers for that actually don't ask for an angle, but that's probably an oversight in my opinion. Okay, let's find our next question. Question 4. Okay, so question 4, we have a table, And in this case, we have a list of displacements, times, and velocities. So they're asking you to use your rearranging skills just to practice defining it. So I'm just going to go through I'm not going to write the whole table out. I'm just going to go through the answers quickly. C, D, E, F. Really shouldn't be any dramas with this one. If you suck at algebra, and sometimes that happens, you want to get better at it, but sometimes it does happen. There is a little triangle we can use to help with some of these formulas. Anything where you've got, say, something equals something over something, we can draw this diagram here. Down, so V will go down here, S will go here, and T will go here. And so now you can see, well, velocity equals displacement over time, time equals displacement over velocity, and displacement equals velocity times time. And you could rearrange that equation to find all those three. It is a little trick just to help. So let's go. Our first two are asking for velocity. Our first one, units are in meters per second. So we've got 200 divided by 10, so that's just going to be 20 meters per second. The second one, though, you've got kilometers and hours. Now, it doesn't ask for SI units, and some of the later ones have their values in kilometers per hour as well. So for this first one, I'm going to do both quickly, and then for the later ones, I'm not really going to worry about it. So let's see. Yeah, if we look in the answers, it is going, well, it's done it in kilometers per hour, and then it's converted back to SI units, which is always a good thing. So let's do that. So 50 divided by 1.5, that'll give us 33.3 kilometers per hour. Now to convert, we divide by 3.6, which gives us 9.3 meters per second. Dividing by 3.6 is a really good little trick to remember. Okay, next one, we need to work out displacement. We can see from our little triangle, displacement equals velocity times time. So our first one we have in SI units, so it's good, 140 times 30 gives us 4,200 meters, or 4.2 times 10 to the 3 meters would be more appropriate. Next one, we have kilometers per hour as the velocity, and we have time in hours, so we can multiply that together, and we'll get our answer in kilometers. Sorry, so that will give us 660 kilometers, or 6.6 times 10 to the 5 meters. Next one, we have velocity and displacement. We want to work out time, so displacement divided by velocity, 300 divided by 15. First one's just going to be 20 meters. 20 seconds. Working out time, that's right. Next one again, we have kilometers per hour in our velocity, and we have kilometers for our displacement. So we can just work them together, and we'll get hours out the end. 130 divided by 65 will give us 2 hours, or 7.2 times 10 to the 3 seconds. Remember, there's 3,600 seconds in an hour. Some of these numbers can just help to memorize. You don't need to, but it does kind of help sometimes. Alright, let's get into next one. 5. An archer can fire an arrow at 390 meters per second. What time would an arrow take to hit a target 100 meters away? Now, if we think about this, an arrow is going to fall down. It's not going to fall much, but it will fall down a little bit. Let's pretend it doesn't, because we don't want to think about how far it's going to fall due to gravity. At this point in this chapter, this is just doing constant velocity type questions. So we have here a speed equals 390 meters per second. We can write it as velocity as well. We're not really talking about direction. If you're comfortable, you can sort of flip between, so 9 is horrible, flip between velocity and speed interchangeably whenever there is straight line stuff going on. Or if you want to pretend that it's actually just a straight line thing, like for example that train track earlier, we could just pretend that it's a long straight line instead for our track in order to use the equations that we've learnt for straight line velocity. But you just need to be a little bit careful. Sometimes it's okay, sometimes it's not. For most of this course, I imagine it's going to be okay. We know that the distance equals 100 meters. And so speed equals distance over time. Time equals distance over speed equals 100 over 390. So 100 divided by 390, and it gives us 0.26 seconds. And as someone who's had a student shoot an arrow at them when doing indoor archery, that seems about right. Scary thing. The highest speed on land in a car is 1,190.4 kilometers per hour. Blah 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 blah. What time would have taken him to cover the 1.6 kilometers test distance? Exactly the same as before, we just got different units. So we've got here, let's write this down. So we have our velocity equals 1190.4 kilometers per hour, and we have a distance or a displacement of 1.6 kilometers. Now we can see here we've got kilometers and kilometers, so that means our answer would be in hours. So again, velocity equals displacement over time, time equals displacement over velocity equals 1.6 divided by 190.4. 1.6 divided by 1190.4 equals 1.34 times 10 to the negative 2 hours. So, well, what is that in seconds? So we multiply by 3,600 because we wanted to convert hours into seconds, and we get that equals 4.8 seconds. Pretty fast. I mean, that's the whole point of it. Question 7. A person rides a bicycle to a shop by travelling 300 metres north along a straight road, then travels west for another 400 metres. If the trip takes 3 minutes, find the average speed, the average velocity. So in this case we are emphasising the difference between displacement and distance. So let's write out the things that we know. We know that the total distance equals 300 plus 400. Don't care about direction. 700 metres. We know the time equals 3 minutes or 180 seconds. Remember SI units. The displacement we don't know yet. The velocity we want to calculate, and the speed we want to calculate. Okay, and the reason I'm putting in displacement is because, well, I've been asked to find velocity. So let's start off with our displacement. Displacement, well, if we draw it, it's going to be, well, 300 north and then 400 west. Oh yeah, we can see it's going to be a nice right angle triangle. Now, there is such a thing called Pythagorean triplets, where the two sides are a whole number and the next hypotenuse will also be a whole number. Recognizing some of these can be good. A 3, 4, 5 triangle is one of those really common ones. So if you see it, feel free to help yourself. If you don't believe me, do the math yourself, but that side is 500 meters. Now, we've got our displacement, which means we can do velocity and speed. Let's work out speed. Speed equals distance over time equals 700 over 180 equals, gives us almost 4 seconds, so 3.9 seconds. Velocity, same, well, sorry, not distance. Displacement over time equals the displacement we just worked out, and we can see well, that's going to be less, which means that our velocity should also be less, and it is indeed. Don't know why I put seconds for that. Meters per second, 2.8 meters per second. Same units, just different type of thing. We should probably get a direction as well. Does it actually care about it? It does. So we need to know this angle, because that's where we started. So theta is going to equal arctan of 4 over 3. Again, I am really shortening the math a little bit there, guys. If you're not certain on how these things are happening, you will need to speak with me in class. And that's going to be north and then to the west there. So our velocity equals 2.8 meters per second at 53.1 degrees north west. Alright, on to the next. Ferrari Testarossa, when driven by an experienced racing driver, can cover 400 metres from a standing start in 14.2 seconds. If it crosses the 400 metre line at a speed of 203 kilometres per hour, what is its average speed? Okay, so average speed, we're looking at the speed, well, we need to consider its start and its finish. So we're looking at the change over the change of velocity, or the what's the best word I'm looking for here? The distance over time is the average, and it's going to be less than that top speed. Okay, we can sort of let's wade into it and I'll show you what I mean. So let's take distance equals 400 meters. We have its time of 14.2 seconds, and we have its top velocity of 203 kilometers per hour, or at least that's the top for this scenario here. And again, let's convert that to SI units. So we've got an easy comparison. Divided by 3.6 gives us 56.4 meters per second. Pretty close. So again, velocity equals distance. Sorry, displacement over time. I know I wrote distance here. We could write displacement as well. You'll find that sometimes it is just sort of easy to cross the two in your head. Equals 400 over 14.2 gives us 28 point, pretty close to 28.2 meters per second. Now, the cool thing is, if you double that, you get about 56.4 meters per second. I've rounded off both my answers here, so it's slightly off by a little bit. But if you've got constant acceleration, which we can assume he's doing here, is that it's just continuing to accelerate, he hasn't hit its max speed, then the average speed will be just half whatever the top speed is. We didn't actually need to calculate the rest of it, we can go from there. So that's only under constant acceleration. What we're essentially doing is going, alright, take the lowest, take the highest, then add them together, and then divide it by 2. If, however, it's not, you need to take a weighted mean, and I believe there's a question later on that will show us that. Okay, let's head on to the next question. Okay, we need to do a displacement time graph. Now we have a bunch of numbers for our time elapsed and for our displacement. They want us to draw it and describe it in words. So I'm just going to quickly plot this out. So we're going to have 0. It doesn't get further than 6 meters away. It goes up in 2. So 2, 4, 6, and up to 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 3, 5, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. No, must have gone too far. Okay, so we've got our graph, at least a crappy graph. I hope you draw better. Let's plot it in. At 0, 0, 1, it was 2. At 2, it was 4. At 3, it was 4. At 4, it was 4. At 5, it was 6. 6, it was 6. 7, it was 4. 8, it was 2. 9, it was back to 0. So, what did its motion? So, 0 to 2, t equals 0 to 2, dog. Running away because displacement is increasing during that period, and we could sort of connect the dots a bit, being as we know this is at 2 to 4, dog still, because displacement time is horizontal. If there's no gradient, there is no velocity. If there's no steepness, there is no velocity. 4 to 5 goes away again. 5 to 6 still. 6 to 9 comes back. Okay, so your dog runs away, stays still, runs a little bit further, stops, comes back. Alright, so that was part A. Part B, and I think we've answered most of these questions. When was the dog stationary? So, dog was stationary at t equals 2 to 4 and 5 to 6. Next question, when is its displacement increasing? From t equals 0 to 2 and from 4 to 5. So when it was going further away, the 6 to 9, the displacement is decreasing because it's coming back to us, so you've got to be careful for that. Let's see, and the last question it's asking is when was the dog moving with the greatest speed? Not velocity, but speed, which sort of clues you in that it might be looking in either direction, because this first part of the graph and here we have positive velocity because it's going away from us. Here, or at least we've defined that these numbers are positive. 2, 4, 6. While these numbers here, they are coming down, and so it is negative velocity. However, speed just cares about the size. It doesn't care about the negative or the positive. And the way you would calculate that is that velocity is going to equal change in displacement over change in time. I'm just going to do this last slope here. We can see it's the change in displacement. It ends at 0, started at 6, so 0 take away 6, and it went from 9 till 6, so 9 take away 6 seconds, which gives us negative 6 over 3 equals negative 2 meters per second. While this section here, it finished at 4, started at 0, and it was at 2, take away 0 equals 4 over 2 equals 2 meters per second. So this bit and this bit are the same, and that bit will be the same as well by looking at the graph, but you should confirm that for yourself. So for D, we would write 0 to, when does it finish? 2, sorry, T equals 0 to 2. Next one is 4 to 5, and then 6 to 9 has speed equal to meters per second. Okay, let's see. Next question, 10. For the graph of a roller skater shown in figure 2.1, that graph there below, calculate his average velocity for each of the 5 sections of the graph. Calculate his average velocity for the whole journey, calculate his average speed for the whole journey. Okay, so what it wants us to do there is to do the velocity and its displacement time, so it's the gradient for each of the bits where they're different. So I'm just going to quickly sketch it. I'm not going to label it, but it starts off going up, then it goes across, then it goes up, then it goes across, and then it comes down. So it wants us to work out the speed for this bit, this bit, this bit, this bit, and this bit. So let's start with the easy bits. Using this label, B and D equals 0 meters per second. It's not increasing, it's horizontal, which means there's no velocity, so no velocity to worry about. For A, let's see, I'm looking at the graph now. I can see that in A it goes up 60 meters and it goes across 10 seconds, so that's going to be 60 over 10 equals 6 meters per second. And looking at the steepness, we can see that the 20 to 30 section, so section C on our little diagram there, is not as steep as the first bit. So we're going to definitely calculate the next one. We can't just guesstimate that. So it goes up from 60 to 100. So 100 take away 60 divided by 30 take away 20 equals 40 over 10 equals 4 meters per second. And then the last section E, we start at 100, we go down to 0, so it's going to be 0 take away 100, and the time it takes is from 40 seconds down to 60 seconds, so 60 take away 40 equals negative 100 over 20 would equal 5, negative 5 meters per second. Alright, So they're all the individual sections. Again, we're just working out the gradient each time. Calculate his average velocity for the whole journey. Well, that's easy. In fact, we don't even need to do any real math for that one. So if you look at this one, he starts at position 0, comes back to position 0. So his delta S is 0. Therefore, velocity equals 0, his average velocity for the whole thing. Last bit, we want speed. And speed is distance over time, so we need to work out distance. So if we have a look at his graph, in section A he starts at 0, goes to 60, then he waits. Then in section C he goes from 60 up to 100, then he waits. And then he goes from 100 back down, so he's gone away 100, yeah, he did it in 2 sections. The waiting doesn't matter. He went away 100, then he came back 100. So distance equals 200. And then as time took 60, speed equals 200 over 60 equals 20 over 6, which is a bit over 3. 20 divided by 6, yeah, 3.3 meters per second. Note, no positive or negative involved. The next section of the chapter looks to be an acceleration, so I think that's a good place to finish this first video. Look for the next video for questions 11 onwards, and there'll probably be a third. Thanks, guys.